Hello, everybody. Right, inextricably linked reproducibility and productivity in machine learning. This was the original title, but it's a bit of a mouthful, so we went for that in the end. So this, I found out last Thursday I was doing this talk. It's a 40-minute talk, and now apparently I've got 20 minutes. So I'm going to try to go quick and keep it understandable, and I guess we'll find out during the questions whether or not I succeeded. Right, so what I'm going to do is I'm going to compare the changes that software development has been through over the last 20 years and how things have improved. And then we're going to look at how we're doing machine learning and how we might be able to apply some of those lessons. So I'm going to need to do a quick survey. Put your hands up if you started your career in software, et cetera, in the 70s, 80s, 90s, noughties, 2010, after 2015. I did this talk in San Francisco, and like 70% of the room put their hand up after 2015, and I thought, well, that's great, because now I can say whatever I want. They're all children. Okay, so let's go back to the late 90s and have a look at software engineering. Now, you'll all be familiar with waterfall, the various silos. There's more silos than this, but traditionally things would be broken into development, testing, and then operations. And what I'm going to argue is the silos arise from crappy tooling and processes, and we'll see how that comes later. So again, some of the things I'm saying today are deliberately facetious to make a point. I'm sure there are people doing this well in the late 90s, but if you look at the long tail of how things happened, it was a bit of a mess. So at least when I started my career, version control was far from ubiquitous. So what would happen is while you were working with your colleagues, you'd make copies of things, and you'd have like, this is definitely the final V2, V3, V4.dll that you would pass around. You'd have code on shared drives, which would often get clobbered. And in general, it was very difficult to reproduce each other's work, which slowed everyone down. But then it gets better, because these days you don't see it as much, but then you'd have specific testing teams. And in the specific testing teams, their job was to make whatever you'd badly collaborated on for a week and then test that it actually worked. But of course, they had the same problem, which is that they found it hard to reproduce things because you'd have all sorts of problems like the famous "it works on my machine," or the fact that there were various final versions of whatever code you created that they then needed to go and test. And this gets worse because not only were they unable to easily reproduce the work that you'd done, but also it happened sort of out of sync. So sometimes there'd be a couple of weeks in between you writing it and them testing it. So by the time they do that, the whole world's changed, and suddenly the results that they're getting aren't very useful anymore. And then, of course, it gets even better, because now once we've collaborated badly, passed it to the testing people who are pulling their hair out because they can't understand how to reproduce the work you've done, we now pass all of this in some sort of final version to operations who are then going to deploy it. But the problem again there is that they're unable to reproduce all the steps that you took to be able to create the software in the first place. So if something goes wrong, not only are they unable to reproduce those steps, but they also don't have the context that you had when you were creating the software in the first place, which becomes very tricky when you have things like performance issues. Now, normally that's a whole, basically theater piece, but we're going quickly. So the question is, if I'm saying everything was so bad in the late 90s, how did we make software? Because obviously there was very popular software at the time, it was making awful lots of money. And the answer is that when you've got crappy tooling and processes, often you see these silos splitting out, and they tend to reinforce themselves. Because we're unable to easily reproduce how things were made, so we're unable to have confidence in the software, so we end up having to choose between speed and safety. And you notice things like change control boards, huge manual documents of things that need to be checked before things are deployed. And the problem with this is that it re-emphasizes the problem that's already there. Because if you have, for example, a manual checklist of things to be done before deployment, humans are going to do that checklist. And humans are crap at discipline, so they will almost necessarily do it differently sometimes. So even the deployment itself will become unreproducible, which tends to slow everything down to a halt. So how do we relate all this to reproducibility? So the whole idea of software on every single level, whether it's you trying to get your unit tests working, or you trying to get CI to go green, or you figuring out what the customer actually wants, is iterative. And one of the talks earlier spoke about the idea of, you want to be able to get something out quickly because it might not be the right thing. Now, when we're unable to figure out not only what the developer next to us did, but then how the testers tested it or how someone manually deployed it, very quickly it becomes hard to do this kind of iteration, because essentially the iteration is just one big scientific method, right? It's like you've got a hypothesis, you can test it, and then you can analyze the results. If you don't really know how you did it, it becomes really difficult to build software quickly. So software development has improved quite a lot, but just in case any of you didn't believe any of the stuff I was just saying, does anyone remember the Joel test? So this is Joel Spolsky. He made Trello, Stack Overflow. This was the Joel test. This was a big deal in August 2000, although people were still seeing this as an aspirational list in like 2006. So in 2006, it was seen as aspirational to have version control, which shows how far we've come in such a short space of time. Now again, lots of companies were using this, but not all were. And what we're going to see later is how, although some companies are doing machine learning very well, most are not. So what's better these days? Well, version control is ubiquitous. There are very few people who start any project in software engineering without first saying like Git in it and putting it in a new Git project. Because of this, developers are able to reproduce each other's work effectively, which means they can collaborate, which means that we can then scale teams in a way that's a little bit more sane. And the same applies to testing, and even ops are getting in on this now. GitOps is the new thing where you put the manifests for everything you want to be deployed in Git, then you deploy it, and then you use monitoring to figure out what the difference is between what you intended and what you've got. So this idea of having reproducibility through version control is now pretty much ubiquitous, or is getting that way in normal software engineering. And the reason why is because version control is the only same way to do reproducibility. If you're copying files, you don't have a shared view of the world. What you have instead is like hopefully a shared view of the world and probably different versions of the world. Now, because we can now version everything, we can then do continuous integration, which is also fairly ubiquitous these days, right? Most people push to some sort of build server, it runs some tests, and then maybe goes ahead and does a deploy. The point about this is that the tests themselves are probably also in version control, and it's being run automatically. So there are no humans in there, and there's no guesswork as to where the test came from, or which versions of the test were running when they ran, which means if they go wrong, we can reproduce that, which is the whole point of the debugging cycle. And then last but not least, we have continuous delivery, which is sort of getting towards ubiquitous, or at least everyone says they're doing it, even though they're not. The idea here is the same thing, which is, well, if we've got some extra work that's helping to get the piece of software we've built from development through testing into production, then that work should also be automated, and the scripts running that should be version controlled, again, so that we can reestablish what's happened if something goes wrong. It's essentially all we're interested in, what happened when something goes wrong. Now, the idea is that if you move from these sort of self-reinforcing silos due to crappy tooling and processes, and move towards an idea where you can quickly and easily reestablish a shared view of the world when something goes wrong, then you don't have to choose between speed and safety. And the ops metaphor for this is moving from a mean time between failure mindset to a mean time to recovery, which is instead of putting in lots and lots of checks and balances to make sure nothing ever breaks, we just deploy stuff all the time because we know when it does break, we can fix it quickly. And this is why we've been able to move from delivering software every 6 months to deploying 1,000 times a day at Netflix. And it's all powered by being able to reproduce all the steps in the stack. So now for the hopefully humorous part. How are machine learning teams doing today? So we've spoken to hundreds of machine learning teams, and the Wild West is the best description we could come up with. We just ran a survey of 500 companies. You can download it there. This quote's wrong, and I realized just before I came on stage, but anyway, let me summarize it. Despite the fact that people are spending inordinate amounts of money on machine learning initiatives, it's still taking them somewhere between 7 to 18 months to get the machine learning models from idea to production. Now, if this were a normal software engineering team, no one would accept that, right? That's just seen as way too long. You'd like to have a prototype within a month. You'd like something that was working pretty well within 6 months. You'd like it to be in production by 12 months, right? 7 to 18 months to get from an idea to production for a machine learning model is sort of bizarre. And there's many reasons why this is happening. One of them is tooling. The other one is awareness, which hopefully we're working on today. But what we did is we took some quotes from some of the customers we've spoken to and anonymized them, and now I'll share them with you. So this is what's going out there in the wild. This is a major Dutch insurer. In retrospect, if we had been able to save the versions or have gone back in time to see how he got his learning rates, it would have avoided a lot of questioning from the auditors. I'm going to see why the auditors get really upset a little bit later on. This is a great one. 2 of the data scientists who worked on that particular model have left and gone to other companies. You want to be able to see what they did, how they did it, and not that it's gone when they're gone. So I can only imagine they walked out with a USB stick or just deleted everything. This is a major US gaming company. One model failed for 3 months and we lost an immeasurable amount of money. Now I'm pretty sure it was measurable. I think what they were trying to communicate was that it was too much. This one's good. After the last audit, so I was surprised by how many problems in the audit we could have solved by keeping paper logs, but if we ask our data scientists to do this, they will leave. And here's my favorite. In order to do collaboration, this company keeps their data science teams in a small room. So, I don't know. I mean, considering that data scientists cost an awful lot of money to hire and that the churn's quite high, keeping them in a small room and asking them to remember doesn't seem like the greatest way to scale your startup. So, I want to introduce this idea of destructive collaboration quickly, although I did mention it earlier. So collaboration can work in many ways, and we're introducing this term of constructive versus destructive. So I would say that constructive is version control, because it means that you can see who did what, when, why, hopefully if they put a commit message in. Destructive is copying things around. So we see training data all over shared drives with no access controls. We see, this is one of the things that the auditors love, people slacking or emailing notebooks to each other, so that, you know, when an auditor turns up, it's like, how did you get that rate? It's like, I don't know, Bob sent it to me, Steve had a look, and then ended up with Amy. Like, auditors hate this shit. Not very much manual documentation, and lots of this, data wrangling. So people just taking huge dumps of data, messing around with it forever, and then leaving it on their local drive, and then emailing it to someone. And then, of course, when the machine learning model goes wrong in production, it's like, well, why did it go wrong? So I don't know. Like, we threw that MacBook away, it got old, we got a new one. Testing's hardly ever done. So testing seems to be like this thing where I'll work on my learning rates or whatever I'm optimizing for a little while in development. And then once that's working, I'll push it somewhere. That's it, right? No centralized testing. There's very little chance that you're going to be able to, what does that say? Oh, it says 10, thanks. Very little chance that you're going to be able to reproduce what anyone else has done in case they leave, or in case there's an error and they're on holiday, or all sorts of very simple things like this. Deployment still seems to be very 90s, in that even if you've got a team of data scientists who are collaborating quite effectively together and they end up coming up with a single trusted, tested model, it'll still typically be emailed to, Sue, and then that'll be deployed somewhere. And it'll be deployed with a huge manual of steps that need to be followed to do it, and a bunch of things to look out for. And nobody reads manuals, so this doesn't work very well. There's also another problem with deployment, which is model drift, which is the guys who lost a measurable amount of money. But I pulled that one out. But basically, we also see a lack of monitoring. So there's a lot of deploying into production and then monitoring things like latency. But if you're predicting whether or not that thing in front of your Tesla is a child, then latency is not very important, right? It's whether it's a child or not that's important. So again, to sort of close the circle, how are we shipping anything with all this mess, right? Now, one of the answers is that there are some companies doing this very well, but most are doing it very badly. And because they're doing it very badly, they're being forced, like 90 software engineers, to choose between speed and safety. And what we see is silos that are growing apart and growing and becoming stronger because people are putting more and more manual checks and balances in between to overcome the fear that this mess that they're working on won't work, which is a very real fear, because it probably won't work. So how do we improve the situation? As I've said a few times, version control underpins all of this, because it's the only way that we can reliably reproduce all the steps in the software stack. We saw how with software development, we've gone from introducing version control in development, and then using it in continuous integration to do testing, and then continuous delivery, and now observability and monitoring. And interestingly, what you'll see is that where you used to have like a development team and then a huge testing team and then a huge ops team, that's very different now. That testing team's pretty much disappeared, which shows how when tooling and processes are correct, the silos become non-self-reinforcing and start to shrink because it's simply easier to automate the people than it is to use them. So let's imagine you want to do reproducible machine learning. Now, most people, when they think about version control and not normal software engineering, think about just starting Git, putting it in GitHub, pull requests, and all this good stuff. But there's a lot more going on in machine learning that you need to take care of. So first is the environment. Now, arguably, this also applies to software engineering. But if you want to be able to reproduce, for example, a training run on a machine learning model, you're going to need to know which libraries it was trained on, right? It also turns out that in some cases you need to know which model of GPU was used. You might want to know what kernel. So all this needs to be captured. Otherwise, if you try to reproduce the same result somewhere else, it's not going to work. The second and slightly more obvious one is the code in the notebooks, including the parameters, although this still isn't happening everywhere. But of course, we're going to need to know what code was used to train the model, right? We're going to need to reproduce this somewhere. And then the really tricky one is data, which is very often what we see is that models are trained on data that can't be found anymore, or that has been altered, which by definition means the original version can't be found anymore, right? So to really say, I can reproduce all the steps in how this machine learning model was created and deployed to production, we're going to need all of this and arguably more, because we're also going to need to know what tests were run on it, we're going to need to know which deployment scripts were used. So it's a bigger issue. Now, there are companies trying to do this themselves, and there are great tools around for doing it, right? So if you want to control an environment, you use Docker. For anyone who doesn't know what Docker is, it controls environments. Let's go with that. We can do an introduction to Docker later on. Of course, if you're going to version control code in notebooks, you can use Git and GitHub, which is very common. But again, now what you're looking at is trying to connect both Docker and Git. So if you don't have DevOps people in-house, that's going to be tricky because who's going to build that for you? We see hilarious things happening with training and test data, but if you're not storing it on someone's USB drive, then some sort of really ambitious people will then put small test and training data in Git, which works perfectly. Git should be able to do everything. Unfortunately, once files get to 100 megabytes or more, it breaks. So then people move to something like Git for large files, which then moves them from 100 megabytes up to 2 gigabytes. That's also fine. But lots and lots of training and test sets are way bigger than 2 gigabytes. So what do you do then? Well, most people then do is they move to Amazon S3. Now in Amazon S3, you then have a different problem because now you've got Docker, you've got Git, and you've got Amazon S3. And it's your job now to make sure that you somehow track all those things relate together, right? So if somebody changes training data somewhere, how does your system know that happened? Now, it's not rocket science, but you're going to be building it, and you've probably got better things to do. The other thing is that once training and test data gets very large, Git LFS and Amazon S3 don't do diffs. So like with Git, we're all used to, if you do a push, it'll figure out only what's changed and send that, which makes everything quicker. And code's small. If you're working on like a terabyte of training data and you change 1 byte, you don't want to be sending a terabyte. And that's what they both do. So this is tricky. So, like I said, people are trying this, but the only people we see winning are like the obvious people who would be winning, which are the people who've had to build this stuff before other tooling was available out of necessity because they wanted to do machine learning at scale before there was any tooling. So our hypothesis at .science is that if you care about machine learning, you're not going to care as much about building all that, so we built it. How are we doing? Oh, yeah, I had 3 minutes ago. Thanks, Steph. That's very good of you. So I'll give you a quick overview of .science. Basically what .science does is it manages the end-to-end workflow for machine learning projects. So it gets involved at the moment that you ingest data from another data source, and then we start tracking all the moving parts in the system. So that's like code, parameters, hyperparameters, environment, training data, test data, GPU versions, anything else you would care about. We then help you to deploy the model into production, and then we monitor it there and push this information back to development. Now, importantly, one of the key design philosophies of .science is that you're supposed to bring as much of your infrastructure as you want. So if you want to use your own CI tool, that's fine. Your own storage, that's fine. Your own compute, that's fine. Your own monitoring, that's fine. So we can act as a spider in the middle of the web and connect all the things you have and provide the tracking, or we can provide those things for you. Underlying all of this, especially for the big data, is an open source tool we released called .mesh, which is basically Git for data, but scales to petabyte scales. So you can ingest data into the development process at huge scales, and then we'll version that for you and track it all the way through the lifestyle so that you have that reproducibility from sort of start to end. There is the question of where you do hand over from data engineering to development, but that's more of a cultural thing. By default, it's embedded Jupyter, but it works with R. What you do is you basically work the way you would normally like to work, but you drop some stuff into your code to tell us what you're doing. So if you're updating a file, you tell us. If you're pushing something to another server, you tell us. And that way we can create a provenance graph, this thing, of everything that's happened. So for any machine learning model that's running in production, which would be the one down the bottom, well, in this case, it's not a model, it's just a file, we can see the exact versions of all the code and data that went into creating that, and then see the versions running back in time so you can see exactly who's touched it, where and when. I'm just going to go to questions because I don't want to pitch the product too much. But the general idea is that whether you do it with .science or anything else, reproducibility of every level of the stack is going to be key to success with any software project, but especially with machine learning projects because there are way more moving parts. And that's it.
Any questions?
Silenced.
Yeah. The thing about versioning of data, so when you get into versioning these very large files, yeah, there's some problems. Yes, it's kind of difficult, right? But those problems aren't unique to machine learning applications. Right? There are other applications that have to version large binary assets.
Yeah.
And the other thing is, applications that have to version multiple unified binaries tend not to have to merge them.
Yes, merging is a big issue. Yeah.
Well, yeah, but is it a real world issue? Like, is there ever a thing where I'm borrowing a 100 gigabyte file, change line of it, and then merge that file back? Aren't those things, by the time you get to a certain size of data file, it's effectively a binary anyway? Like,
Yeah, arguably. I mean, if the definition of binary is unreadable, then then yeah.
Then the merge problem goes away. You know what I mean? You never have the same. Versioning is still a thing, but actually collaborating on a 100 gigabyte file is not a thing, is it?
Well, I don't know. I don't think so either. But then we did this project with a large consultancy who are looking at barrier reef photos to try and figure out what's happening with it. And they're just massive. Some of them are videos, and they do that quite a lot. So they'll actually go in and edit frames out and move them around and stuff. And that was a real use case. I mean, one of the things that we see is that most people who start using .science will start using something like GitLFS or S3, and we'll just merge with that. But if you want to, like they did, then you can use the underlying open source .mesh that we use to do all the fancy file stuff. But it's not really like, it's not like 70% of people need that. But some people do, and when they do, it's a real problem.
Let's say that you're dealing with sensitive data.
Yeah.
You have a big model that uses multiple sources of such data, and you need to store the data in a database, so you have like a user and a password for all the sources. How would you source control those passwords and credentials?
Yeah, so typically what we've done there is to take the credentials across into the access for the data in .science. So we're not going to like version control the whole database. We're going to ingest whatever you want and then start managing it there. And then you do indeed have to manage permissions in two places. But the way we've done that is just by pulling in the same user credentials and applying them to the role-based access on our side. Does that make sense?
To manage automation, would you recommend using Azure DevOps or GitHub to try to version control?
Right, so that's one of the pluggable things, is that if you want to use the Azure CI, you can do that. Yeah, I mean, it works with Jenkins, Drone, Travis, the Amazon one. So my recommendation would be, if you're already using that, I would keep using that. Because if you're using the Azure DevOps tool, it's probably embedded to other areas in the company. And you're not going to want to pull all that out and inconvenience other teams just because you've got a shiny new tool.